I welcome you all on behalf of JSPM's Rajarshi Shahu College of Engineering Department of ENTC. I'm Vaishali Kulkarni. So I welcome today's speaker, Dr. Mrs. Varsha Harpale ma'am, to day 11 of session 2 of AICT sponsored 2-week online faculty development program on artificial intelligence and its application in biomedical engineering. I take this opportunity to introduce today's speaker, Dr. Varsha ma'am. Ma'am has pursued her PhD in ENTC of Biomedical Signal Processing. Presently, she is working as Associate Dean Quality Assurance and as Associate Professor at Pimpri Chinchwad College of Engineering, Nigri, Pune. Ma'am has the experience of 20 years and her area of interest is biomedical engineering, signal processing and embedded system. Ma'am has the academic experience of 19 years with the job profiles as associate, dean quality assurance, PG coordinator, IQAC coordinator, ISO, chief coordinator of the institute. Ma'am has to her credit a number of achievements like she is the best level finalist for Avishka 2018. She has bagged the best paper award for 2 papers and her research contribution includes a book which is in process that is publication by elsewhere, brain seizure detection and classification using EEG signals. Ma'am has published a book of that is applied statistic in research methodology, a practical and scientific approach, CRC Press publication 2019. Ma'am is associate editor of National International Journal of Advanced Engineering and Technology. She's also the track chair for Health and Hygiene International Conference on Computing, Communication, Control and Automation. Ma'am was the speaker for the topic biomedical signal processing case study and advanced paper searching for effective literature survey. And also she had been the reviewer for International Journal of Biomedical Signal Processing and Control by Springer and International Conference on Sensor Networks and Signal Processing in the University of Science and Technology, China. Ma'am has 2 credits of copyrights registered and also 1 patent published. So she is having publications of 30, which includes 2 SCI, 15 scope, others. So on behalf of JSPM's Rajarshi Shahu College, we welcome you, ma'am.
Thank you, ma'am.
So I request ma'am to take over the session. Over to you, ma'am.
Thank you. Thank you so much, ma'am, for the nice introduction. So, all of you, very good morning to all of you. Hope you are enjoying this treat of biomedical engineering and its application during this workshop of artificial intelligence and its application in biomedical engineering at RSCOE, and it's in coordination with AICT and other. So thank you so much for giving me this opportunity to explore concepts related to the seizure detection, prediction, classification using EEG signal. Basically, I would like to talk on to the EEG signal itself. Okay. So just give me 1 second, please. Okay, my screen is visible, ma'am?
Yes, ma'am. Yes, ma'am.
Okay. Okay. So we'll start with this. Basically, the total area that I will be covering under this topic is related to the EEG signal processing. And it's a very good journey that I had to work with this topic of seizure detection and got a very good experience to work with this topic with lots of credits in terms of publications and all. So these are the contents for my today's topic. So basically, we have started, once we'll start with any topic to search of that, what are the areas that we would be looking forward for. So that is what is research areas in brain analysis. I thought that I'll work with this brain sort of things, or you can say neurological disorders. So the challenges that I need to first identify, the areas that I need to first identify. So that's why we can say that we will be starting with this research areas in brain analysis. So if you look forward for the research trends in brain analysis, you'll find various brain disease detections and prediction. Various work is going in the area of brain disease and detection and prediction. The human emotion analysis, motion tracking, automated detection of neurological disorder, neurological events. Similar way, certain what we can say emerging research demands is even though the research is going in above areas, we require to have certain things that is to be come up, that is should be the outcome of the research. And the very first thing is that is about the early detection of brain disorder, which is very challenging because the EEG of brain, or you can say the brain signals are very random and non-stationary. So early detection of brain disorder, that is early identification of patient, that will be a biggest challenge. Next is about we require to have certain software tools or hardware tools analyzing a brain, and that's why advanced tools in brain analysis. Simple architectures for brain signal analysis. Basically, you might be knowing about a system that exists in the market that only have a EEG or any of the imaging recording. It doesn't have any automated analysis systems. So if you could able to come up with certain architecture which can be appended with the existing measurement systems as analysis based architecture, that would be beneficial for the rural areas. Because what happened in the rural areas, machine do available, but experts are not available. So if a machine could provide certain initial level analysis, that will be really helpful. So next is about a brain machine interface. You know, it's a very recent area that we have and in which various work is going on. So I would like to move towards the neurological disorders, and I have taken a help of WHO 2015 report for this particular statistics that I'll be presenting in front of you. So very first is about neurological disorders. If you look forward for this report of WHO presented in 2015, it found that we are underestimating these neurological disorders. So providing a rough estimate, about 30 million people are there with the neurological disorders. And it is estimated that the particular neurological disorders or impact of neurological disorder will increase 12% from the year 2005 to 2030. So still there is a chance that we could able to reduce this what we can say number by some value by providing our engineering research in the field of neurological disorder. So if I look forward for the statistics comparing all other diseases, now I haven't included a COVID-19 over here because that is a recent thing that we should add. But this I am referring is from the 2015. That's we taken a major diseases in this particular chart. So if you look forward for this, you'll find out the highest impact of neurological disorder is about 6.3% of the global burden of the disease. So we'll find a disability adjusted life years in a human, or like their total lifespan, this percentage of the people who are surviving, who are striving to survive with this DLLYs, that is called disability adjusted life years. And that is all because of the neurological if I look forward for neurological disorders, it is about 6.3% of global burden of disease. Right. So it's a big count that we should take further and try to reduce that and try to help these people who are really having these neurological disorders. So you might be knowing all the neurological disorders, but this pie chart, which is presented by WHO, it shows that most of the neurological disorders that is because of the brain stroke, and you might have heard in your life also that somebody have died because of this stroke. Then that's why the death rate, which is shown in the second chart pie chart, is high for the stroke. Whereas for other diseases also there is an impact of this that is disability as well as a death. So that's why we should work in these areas so that we could able to come up with certain automated solutions to either predict or detect or helping by guiding by some of the what you can say terminologies to these patients or as well as the doctors so that we could able to come up with certain research certain what you can say reduction in the particular disorders rate. Okay. So, if I look forward for the IEEE publication from 1960s to 2018, this is the thing that I have understood that when we look forward for the human neurological disorders, we find most of the engineering research is going in the area of the stroke and stress. As previously discussed, most of the death and most of the disabilities because of the stroke and the stress. That's why engineers have already worked on to the stroke and stress and have already come up with the good solutions to provide it for the doctors as well as the patients. But if you look forward for other categories of disease like epilepsy, Alzheimer, and depression, certain now this is the years last 2 decades a good research is going in these areas of epilepsy, Alzheimer, and depression. Similar way, we need to go for the Parkinson disease, brain tumor analysis, brain injury analysis, spinal cord injury analysis. These are some of the research areas that we should look forward. And the very needy things in this neurological list about a dystonia, migraine, sclerosis, autism spectrum analysis disorder that you know most of the thing that is available in the children's very lower age, and it is by birth or earlier to birth also that child or infant get affected by this autism spectrum disorder. Cerebral palsy, so this is also one that is a paralysis. It's one of the things that happens because of the neurological disorders. 80% the thing that this paralysis occurs because of the human neurological disorders. So I invite all the people who are there in the workshop to work in these areas because this is a very needy thing that we have to work it so that the overall burden we can able to reduce or we can provide certain share and can come up with some good solutions. Okay, I'll be working in this EEG. So sorry for that alignment. Okay. So brain signal measurements and methods that we have for the brain analysis are, these are the certain methods that you could read: EEG, MEG, fMRI, NRS, PET scan, SPECT, ESI. These are the things that we can have, and we can choose any method which is appropriate as per the disease. Okay. Ma'am, hope I'm clear. Any issue? So, no, ma'am?
No, ma'am, it's okay.
Okay, thank you.
Voice is clear. Voice is
Okay,
clear.
thank you. So, if we compare the various methods that are available to look forward for the brain analysis, we could see this chart and we can find it when we look forward for the temporal and spatial resolutions of these methods. Some of the methods are good in temporal resolution, some of the methods are good in spatial resolutions, and both the things are important for us when we are looking forward for the full brain analysis, right? So if you look forward, the EEG is one of the method that is having a good spatial resolution and medium or temporal resolution, and simplest to work with it for the analysis. That's why the preferable method that we have, cheapest also, that can be work for the brain analysis. So we can enlist some of the advantages of using EEG. It is a non-invasive method. It is invasive also, available for the invasive, but not an analysis. For surgery, we used to prefer for the invasive method of EEG. This is very simple, simple in the sense of repetitive things that we have to work for the multiple channels, and we could able to easily come up with certain solutions. So it has a good spatial and moderate temporal resolution as we have seen in the earlier diagram. So now I would like to proceed further for the EEG signal processing, and I'll definitely return to the EEG prediction as mentioned in the topic of my schedule. So EEG signal processing and analysis. So when we look forward to the brain, we already know that the brain will be divided into these sections, and each of the sections will be having a different functionality of the human body. Now, normally when we look forward for EEG signals, there will be a 10 to 20 standards is preferable, and by which we used to place the various sensors on our brain and we used to record this EEG. But we find some challenges in the EEG signals, like small signal amplitude, specificity. Small signal, it's just available in 0 to 100 microvolts. Okay. So whenever we are looking forward for any signal which is having very low amplitude, the first thing is the separation of that signal from the noise. And that's why we need to work hard to go for this particular small signal amplitude. We need to address this particular challenge. Next is about the specificity. If we would like to understand the neurological, or we can say brain conditions, we have to connect these sensors all over the brain. It's not easily could able to understand that where is the area that get affected by this disease or this abnormality. Next is about the sensitivity to noise. A very important factor in EEG that we need to consider, these are artifacts. Artifacts is because of the normal routines, or what we can say the inhibitory actions of a human body will create an impact onto these EEG signals, and that's what we call it as artifacts. And real-time analysis recording, you know that if I would like to record a EEG, I need to wear the cap. I need to wear the sensors, right? And if I would like to wear the sensors, I cannot carry that sensors or the machine with me. So I have to have certain of the, what I can say, handheld solution, which can be provided for the real-time analysis and classification. So most of the work is going in the last point of this challenge. So this is the brain structure. I would like to highlight this because whenever we would like to work with the EEG, we need to first understand about the mathematical model of it. And mathematical model should be always analogous with the behavior of that component. So that's here we are taking case of the brain. So behavior should be understood, and then only we could able to come up with certain mathematical model or certain measurement systems. So this cortical column, just give me a second. So this cortical column that if you look forward, this is the representation of the behavior of the brain. And we could see that each of this neuron, they are connected in a vertical fashion or column fashion, and these are called columns. Okay, and these columns will be connected in such a fashion that will be divided according to the lobe structure as well as its actual functionality. And whatever EEG signals that we will be looking forward for, that will be recorded, and we could able to read them through the sensory inputs. Or we can say this is what the sensory inputs to cortical column, but we could read this cortical columns, and we could able to understand what happens with the inputs given to this cortical and how they behaves and excites because of this what we can say, or what we thought that we have at that instant, or a human body condition that we have at that instant. So that's why these cortical columns are taken in a system, and we should connect the sensors to it. And these sensors we are recording with the EEG measurements and equipment systems, and we will be having this EEG available outside. So I would like to just explain what can be the contents that is there in the EEG measurement. So input signals, that are the channels that you are going to connect it to your brain. The brain system, so these are the inputs. This is not a brain. This is the input that we are having in a daily life. Your brain react with certain part of the columns, okay? And this brain reacts always in terms of the average. And these averages can be recorded using the sensors through this gain, that measurement system, where it contains the gain, filters, sampling, and then we could able to come down to the digital signals or the sampled signals of EEG, which is available at the output side for the recording, right? And this is what we will be taking further. And very important potentials we observe that need to be taken in consideration when we are dividing the signal into certain information. And this is first we call excitatory postsynaptic potential and inhibitory postsynaptic potential. Excitatory is the reaction potential that we have in case of EEG signal. Inhibitory is your eye blinking, or you can say artifacts for EEG signals now, but for the behavioral things like whatever you normally behave, that is closing of eye, while speaking, whichever muscles that will be having an impact, that things will be coming in the category of the IPSP. And now we will look forward for EEG signal processing. So I've used epilepsy data set, okay, the scattered data sets for my work. And very first data set I've started with a very small amount of patients, that is about 5 patients. And this data set is available online. You can definitely use this data set, which is most commonly used. And at the end of the research, you need to compare your work. So you'll find most of the publications uses the same data sets. So it will be easy for you to compare your what you can say the work with the existing work. Next data set that I've used is about a CHB MIT database. It's a scalp database, and this is for the 20 patients. It's actually for 23 patients, but I could only use it for 20 patients. Okay, and the next one is on request. This data is not available online. It's called a Temple University Hospital data set. And this data set you can able to go get it on the request. So you need to send a proposal to them, and once they'll accept your proposal of working with it, they has to give you the access to this data set. So this is available to you. You can go on. This is a very huge data set. You could see 700 plus patients, 2000 plus files that are available in the category of not only epilepsy, but the category of the epilepsy also. that is epileptic seizures, get divided into certain small categories or classes. That is also available in this data set, which is sampled on the 400 hertz. The sampling tray is also very good. Because of that, you can rely on to your work. And lastly, the verification of my work is done with a real-time data set, and that is by Dr. Pandey, Amit Kumar Pandey. He's a neurologist, and he have provided me a data for the non-labeled data where the particular work is validated. So very firstly, what we should do it is about to remove certain noise, whatever noise exists in the system. And very firstly, the noise exists in the system is about the power line noise. Okay, so you should do some filtering, bandpass filtering. You should find some good order which will affect your part. So let's take an example that if I'm taking a channel 10 and I would like to understand the power, the spike that is occurred at the 60 hertz. So that I need to remove, and you could see that the successfully that spike is removed in this. Okay, by applying the proper notch filter for this, and you could able to go with this removal of the noise. Now next part that we need to do it with the EEG is removal of artifacts. Artifact stands for whatever daily day-to-day routines that we have that actually generates an impact on, or you can say vice versa. The EEG signals controls these things, and because of that there is a variations in your EEG signals, and these we call it as artifacts, and these are like blink artifacts, chewing artifacts. Okay, for my case I need to work with these, that is about a blink and artifact, so that's why I use independent component analysis for this. Is all this particular work is already published, and you can refer that. So EEG signal processing, the next thing is as is the signal processing. We have to work onto the windowing. We have to rely onto this so that we could able to understand some stationary part of, considered to be stationary part of the any signals, because we know that EEG is a non-stationary signal, and we could able to go on identifying, go on analyzing that particular signal by considering that they are temporarily stationary. So that's why the windowing is a method that we used to use. So we can able to go on normal windowing method, or you could able to go with the overlapping windowing method. The preferable things for the EEG that I have come across, that is about the rectangular window. The handing window is a preferable window that we can use it for the windowing technique. I've used rectangular window throughout the work, so I'll not mention that again. But this is the thing has given me a good results to work with it. So EEG signal analysis that is made for the seizure detection, that will be in the terms of time domain analysis, frequency domain analysis, and time frequency domain analysis. So these are the three factors, these are the three analysis that we can use it to understand the EEG behavior. And now I would like to start with, because I could not go to directly prediction. I will be discussing the seizure detection first, and then I'll talk into the prediction. So the challenges that we face if you would like to work with the seizures or epilepsy, these are detection, detection accuracy, prediction of the seizures, the classification of the seizures, and next and very important is about a psychogenic non-epileptic seizure detection. See, the PNES are not the seizures that occurs in the epileptic seizure. Basically, why the lowest one is having a higher priority now? No work is done in the psychogenic epileptic seizures. So it's a good point that can be taken up by the research scholars, that they could able to segregate the seizures as epileptic seizures and non-epileptic seizures. You try to search, you will find very less amount of, and it's the biggest challenge while selecting a topic in a research that is about which should have a good scope of improvement. So if you could able to understand the classification of epileptic and non-epileptic seizure, in that case you will be contributing very good to the society, because when any person who is suffering from epilepsy visits to any neurological person or neurological clinic, he will be first treated as he will be having epilepsy, and they immediately start with anti-epileptic drugs. Okay, and whatever I have studied till now, these anti-epileptic drugs will not cure their non-epileptic seizures, as well as that will lead that patient towards the paralysis. Okay, so it's very important, or they cannot sustain with this antibiotics. So we need to go for providing certain solution or some algorithms which can segregate, which can separate This epileptic seizures and non-epileptic seizures. Psychogenic non-epileptic seizures are because of the stress. So because of your psychological imbalance, these seizures used to be there. But non-epileptic seizures can occur any point of time. Like you might have experienced by yourself also, when you have a very high fever, at certain point of time you got the immediate pain in your brain at certain point. Okay, these are absence seizures. Okay, that are non-epileptic seizures. Okay, so that can happen to any person anytime, and they are not a disorders kind of things. They are just some of the irregularity happens in your EEG or the brain, and that can come up with. But some people will get affected. Means some people has to face this non-epileptic seizures n number of times. That is, the frequency of these non-epileptic seizures in them and duration of that is very high, and because of that they land up into the seizures. Okay, means a seizure disorder is what we can say. So what I did is I've taken that particular what we can say data set and done this time frequency analysis, extracted the features using time frequency domain features, then spectral features using wavelet transfer of DB4, then spectral features using EMD, and spectral features by combinations of this TFT and EMD. Okay, and then I've classified this feature using this machine learning classifiers, and I could come up with a good performance. So for time frequency domain feature extraction, we can go with the feature extractions of time as well as frequency. Then the next very important thing that we have to do, it is not all the features are important for us. So to reduce the complexity of your algorithm, always we need to look forward for one more important problem, that is about a dimensionality reduction problem, right? So we have to go for feature selections. So there are n number of methods that we call wrapper methods and filter methods that are available. This is a statistical method, analyzes statistical methods that I have used, or a hypothetical method that we can say it's used for selecting a feature. And after selecting whichever is having a highest relevance with the class of normal and Caesar, I need to select that particular feature. So that is done by ANOVA. And final set of features that I got it is AVM, VR, or these are just simply time domain features. So that's why you'll find, otherwise there are near about 100 plus features that are available to extract from the EEG signals. You need to find out, if I am looking for epilepsy, which of these 100 features are useful for me to detect the epilepsy or a seizures, epileptic seizures. So accordingly, I have taken 100 features, and from that 100 features come down to some less number of features, and then reduce the feature space, and then come down to the classifications. So that is being done for every set of experimentation. So the next thing that we have is about a wavelet transform. I don't know what happens with this. Can I able to? Okay, fine.